Have you ever wondered what it would be like for our solar system to reside in a nebula like this one? Glorious colours with huge structures stretching across the sky. It must be a pretty cool sight. Well, depending on how you define what a nebula is, it may surprise you to find out that we are actually inside of one, called the local interstellar cloud. How can this be? Well, let's understand first of all what a nebula actually is. The term nebula is a blanket term for a variety of different things. The word is a relic from early astronomy, where everything that looked a bit milky, foggy, or cloud-like was called a nebula, including what we now know are galaxies and star clusters. However, these days, we do have a bit more of a handle on what we classify as a nebula. The most famous type of nebula is the H2 nebula, an emission nebula like Orion, which consists of ionized particles, predominantly hydrogen. They are emission nebula because they emit their own light, as ionizing radiation from the young stars found in the middle of them excite the particles to higher energies, much like a neon lamp. On the other hand, there are also dark nebula, or molecular clouds, where there are no nearby stars, so ionization is not taking place. They often consist of dust and molecular hydrogen. Sometimes you can have a mix of the two nebulae, a dark nebula found in the middle of an H2 region. In such a situation, you can often see the outer particles becoming ionized, with the cold particles still found towards the center. It is especially in regions like these, where dark nebulae become eroded by ionizing radiation, that stars can start to form. In another situation, you can have light from stars shining on a dark nebula, but the energy isn't enough to ionize the particles within it. In this case, you have a reflection nebula, a nebula that simply reflects the light shining on it. The next two types of nebulae are also related. Planetary nebula, where a low to medium mass star has begun to shed its atmosphere and outer layers during its stellar evolution, usually before it becomes a white dwarf. The second type is a supernova remnant, usually the remains of a high mass star after it went supernova, leaving behind a black hole or a neutron star in the center. These two types of nebula are so colorful and pretty because they also consist of ionized particles, charged from the respective events that caused them, so they are a type of emission nebula. Eventually, they will dim and disperse. Now, as you can see, all these nebulae can be categorized into two groups: emission nebula and dark nebula. These two categories have one big similarity: they are all diffuse nebulae. They extend for sometimes up to thousands of light years, and the particles within them are extremely spread out. Some of these nebulae only have a few particles per cubic centimeter, although some can have hundreds. But that still means that an Earth-sized nebula would only weigh a few kilograms. To give you some real perspective, sea level on Earth has 15 quintillion particles per cubic centimeter, and 450 kilometers up, which is slightly higher than the altitude the ISS orbits, there are still 50 million particles per cubic centimeter. So, when we see a nebula, we have the advantage of squeezing very diffuse objects into quite a narrow field of view, which means for objects like Orion, we probably have a better view of its structure than what any locals would have from the inside, because for them it's a lot more spread out. Chances are that if you were on an Earth-like body inside of a typical nebula, you wouldn't be able to tell you are in one with your naked eyes. That's not to say that all nebulae are equal though. The Tarantula Nebula, found in the Large Magellanic Cloud, is said to be such a bright H2 emission nebula that if it were to be where the Orion Nebula is, it would cast shadows at night for us and be visible during the day. A nebula this bright probably could be visible if you were inside it. As for our own local interstellar cloud, it too is an emission type nebula. likely a very dispersed supernova remnant nebula mixed in with some cold neutral atoms. The ionized particles within it are exceptionally hot, around 6,730 degrees Celsius, with some particles even approaching millions of degrees Celsius. However, its heat-specific capacity is very low, because the density of particles is so sparse, at only 0.3 particles per cubic centimeter, meaning being out in the middle of it would barely heat you up at all. Unsurprisingly, this extreme sparsity of particles means our local interstellar cloud is not very bright. In fact, it is very hard to see at all, even with the most powerful of scientific instruments. That's because it really is on the boundary of what you might call a nebula, although we are starting to find out that, like the spectacular images of nebulae we already know, it too has a structure. This cloud is about 30 light years across, and interestingly, we seem to be moving through it, and will likely leave it altogether in about 20,000 years. That's because the Sun seems to be taking us in this direction, while the interstellar cloud is heading this way. So, if you've ever seen images of the solar system interacting with interstellar wind, it's not just the particles that are blowing around our solar system, but it's also a combination of us moving through it. The magnetic field of the Sun pushes ionized particles around the entire solar system, leaving behind a magnetotail as it travels, like a wake following a boat. While we don't have a real visual image of that for our own Sun, as again it's hard to see from the inside, we have seen it elsewhere in the galaxy. However, it's only ionized particles that interact with our Sun's magnetic field. Non-ionized neutral particles pass right through the magnetic field, going right through our solar system. This is how we've been able to tell which way the interstellar wind comes from. We've had spacecraft in orbit detecting the direction of these neutral particles as they pass through. Even though the interstellar cloud is not dense compared to other nebulae, it is actually one of the densest regions for hundreds of light years in any direction. This is because it is contained in a region known as the local bubble, where the average density is even lower than the local interstellar cloud at 0.05 particles per cubic centimeter. Interestingly, this bubble connects two other bubbles, and it's in the regions where these bubbles meet where it's believed that clouds like the interstellar cloud form. Let me explain. When we talk of nebula of any kind of density, we are actually talking about the interstellar medium. The interstellar medium, simply put, is all the gas and dust found in the galaxy, in whatever form that may be. It isn't evenly distributed, and the thickest sections of it are the different types of nebula we have already talked about. However, if you look anywhere in the sky, and look through the right wavelengths, you will see a faint glow in space. These are ionized particles emitting electromagnetic radiation in a variety of frequencies. So, the local interstellar cloud is part of the interstellar medium, but as I mentioned, it isn't evenly distributed. Within our local bubble, the density of the interstellar medium is far below the average of the whole Milky Way. This is because these bubbles are thought to be the result of supernovae explosions millions of years ago. The supernovae not only ionized the particles, it also pushed most of them outward, leaving behind the bubbles, or what is known as supershells. When supernovae shockwaves meet, the particles suddenly have nowhere to go, so instead they clump up. It is believed that our own local interstellar cloud comes from where our own local bubble and another bubble met. There are plenty of bubbles out there, and the resulting local map of our galaxy's interstellar medium looks quite messy. You may wonder though, why is any of this important? What's the point of scientists trying to figure this out? Well, it is important to understand our local space environment because it helps us better define the universe around us. When we are observing something far away, we can remove contamination from any readings caused by the local interstellar cloud surrounding us, because we now know what we can expect from it. Also, Better understanding the interstellar wind coming into our solar system means we can better protect astronauts against it. So, there we have it. While we may not be in a nebula as spectacular as something like Orion, we are right in the middle of our own local interstellar cloud, which has a structure and that emits its own light. Thanks for watching. Want more Astrum answers? Check the playlist here. Also, a big thanks to my patrons and members for supporting the channel. If you would like to help pick the next Astrum answers and join other polls too, you can support the channel by joining. Find the links in the description. All the best and see you next time.